Imagine humanity capturing almost every drop of the sun's energy, using a colossal, artificial structure built completely around our star. It sounds like pure science fiction, but respected physicists have seriously explored the math behind this exact concept. Could humanity actually build a Dyson Sphere? To understand why we might need to, we have to look at our power grid. Our global energy consumption grows heavier every year. Astrophysicists measure this kind of growth using the Kardashev Scale, a method of classifying a civilization's technological advancement based on the amount of energy they can harness. Right now, we extract fossil fuels and harvest the wind or sunlight that hits the Earth. To climb to a Type 2 civilization on this scale, a species has to master the total energy output of its parent star. This animated scale compares Earth's total global energy consumption against the sun's continuous output. Every single second, our star produces approximately 3.8 times 10 to the 26th power watts of energy. We currently utilize a practically invisible fraction of that power. By relying entirely on the limited resources found on our planet's surface, we are letting a near-infinite, star-sized nuclear reactor slip through our fingers. Physicist Freeman Dyson recognized this massive gap in efficiency back in 1960. He proposed that an advanced civilization would inevitably build a megastructure to capture that escaping stellar energy. Popular culture pictures a solid shell encasing the sun, but a rigid sphere is physically impossible. It would crumble under gravitational stress. Instead, the scientifically plausible design is a Dyson Swarm. Billions of individual solar harvesting satellites forming a dense, coordinated orbit. Breaking the structure down into a vast fleet of independent satellites shifts the concept from an impossible fantasy to a problem of manufacturing and coordination. We wouldn't build a megastructure like this overnight. It requires a slow, generational expansion, launching a few satellites at first and steadily scaling up over centuries or even millennia. Earth's crust does not hold the mass required to manufacture billions of solar collectors. To get the metals and silicates we need, we have to look outward to the asteroid belt. Mining millions of tons of rock in deep space means deploying heavily specialized, autonomous robots. These machines would land on asteroids to extract and refine the necessary raw materials directly in a zero-gravity vacuum. Coordinating millions of these mining drones across vast stretches of empty space is too complex for human controllers on Earth. We have to rely on advanced artificial intelligence to manage the logistics of this supply chain. The refined materials are then fed into self-replicating space factories. These automated orbital foundries would rapidly manufacture new solar collectors and, crucially, build exact copies of themselves to multiply the production rate. Sourcing materials off-world and relying entirely on an automated robotic workforce removes the heavy constraints of Earth's gravity well. The construction of a massive satellite fleet becomes a solvable equation of supply and replication. Building the satellites is only the first phase. Keeping the swarm functional over long timescales introduces extreme physical challenges. Coordinating billions of independent satellites requires flawless orbital mechanics. A single miscalculation could trigger a catastrophic chain reaction of high-speed collisions, destroying the entire network. Once the energy is successfully captured, we have to figure out how to send it back. The swarm must convert the harvested solar power into highly focused lasers or microwaves and transmit it efficiently across the solar system to receivers on Earth. Then there is the thermodynamics problem. A massive network of machinery absorbing solar radiation will generate astronomical amounts of waste heat, which must be safely dissipated out into the cold vacuum of space to prevent the swarm from melting itself down. The required materials, coordination, and heat management are immense hurdles, but they are strictly engineering problems. None of these challenges violate the known laws of physics. If the physics allow for it, we have to ask a broader question. Have other advanced civilizations in the universe already built them? This chart shows an infrared spectrum. When scientists search for alien megastructures, they look for unusual infrared waste heat signatures, like the anomaly plotted here. A massive swarm surrounding a star would absorb visible light and re-emit it as a highly specific frequency of heat that modern telescopes can detect. Astrophysicists have flagged several unusual stars, showing strange dimming patterns or excess infrared radiation. However, after careful observation, no confirmed Dyson sphere has ever been discovered. The current absence of confirmed alien swarms makes humanity's own theoretical capability to build one a central question in understanding our place in the universe. So, to answer the original question honestly, no, humanity completely lacks the technology, resources, and coordination to build a Dyson sphere or swarm today. But if our species survives long enough to achieve extraordinary advances in space imagery, robotics, artificial intelligence, and energy engineering, a Dyson swarm is entirely possible. Imagine a distant future where our descendants stand on a planetary surface and look up at the sky. Instead of seeing a lone, burning star, they look upon the greatest machine ever created by humanity. If you want to continue exploring space, astrophysics, futuristic technology, and the greatest mysteries of the universe, make sure to hit subscribe. The blueprint for a Dyson swarm is more than an energy project. It represents the potential transition from a species bound by its planet to one that thrives on the total output of its star.